Hey guys, Mr. Smith here, and we're shooting our second lesson of Unit 7. In this lesson, we're going to learn some other techniques for solving exponential equations. And for a lot of you, I know, like I'm teaching this course right now, the 3U course. Your first experience with an exponential equation usually comes when exponential decay is introduced, and the class talks about half-life. Um, and I won't read the introductory paragraph word for word. But in your grade 11 course, you're introduced to this idea. Maybe you've seen this idea in chemistry or physics. But radioactive substances are constantly emitting particles, transmutating into other substances, and we call the half life of a substance. It's the time it takes for that substance to decay to half of its original amount. So if you had 100 milligrams of something, the half life of that substance would be, well, how long does it take until there's only 50 milligrams of it left? And where the other 50 went, that's a matter for chemistry and physics. And then your grade 11 course, you modeled this kind of function with an equation like so, where you had some initial value, a naught, and you have a base of, in this exponential function, a half for half-life. Things are decreasing by a half. And then because it takes a certain number of half-lives, or a half-life to decay by half, you have t over h in the exponent. H is the half-life. So this h dividing t by h essentially stretches your function so that it decreases by half every half-life period instead of every 1 year if it was just t by itself. So let's actually look at an example. This is kind of a typical question you might see in the grade 11 course, or you might have seen, except in the grade 11 course, you guys didn't have these tools for solving exponential equations. Would have had to use systematic trial and error. But now we do have tools to go at these again, so let's do it. So we're looking at polonium 218 in this question. It spontaneously decays into lead 214. So it shoots off what we call an alpha particle and 2 neutrons, 2 protons. You don't care about this. You just want to do the math. After 1 minute, a 100 milligram sample of polonium 218 is placed into a nuclear chamber, and only 80 milligrams of it remains. What we're interested in finding is how long will it take to go from 100 milligrams down to 50, because that's going to be the half-life of polonium 218. So let's go at this. So let's start by using the decay equation. So let's set this up. Use my purple here. A of t equals a naught times a half times t over h. Okay, and what do we know? We know the um, uh, final amount, which is 80. We know the initial amount, which was 100. And because in this question, we'll let t be the number of minutes after 1 minute has passed. 1 over h. So what we'll be doing, so we want to solve this equation for h essentially, and that'll give us the half-life. And we're going to be solving for h. And just note when we get the half-life, because we use t in minutes, the half-life will be in minutes too. And as I said, in grade 11, you might have got here or something like this and had to use systematic trial and error. But now we actually can go about it using logarithms. So let's actually go about this using logarithms. So we'll divide both sides by 100. That gives us 0.8. And then maybe we can change 1/2. You guys are okay with this? We'll change 1/2 to 0.5 to the power of 1 over h. And we now have a tool to getting at the 1 over h in the exponent. We're going to take the log of both sides. So the log of 0.8 equals the log of 0.5 to the power of 1 over h. And we have our nice power rule for logarithms. Don't really need the brackets for that one. Log 0.8 equals 1 over h times the log of 0.5. Don't need that those brackets anymore either. And we can solve this equation for h. If we multiply up the h, we get h times the log of 0.8 equals the log of 0.5. And then we can divide both sides by the log of 0.8. We get h equals the log of 0.5 divided by the log of 0.8, which is exact. But, let's get this in something that we can actually interpret. Log 0.5 divided by the log of 0.8. And when you do that, you get about 3.1. And again, this would be in minutes. So this kind of makes sense because after 1 minute, it lost about 20%, right? Because it went from 100 down to 80 in 1 minute. So 3.1 minutes seems to fit pretty well. And we can wrap this question up. Half-life of polonium 218 is about 3.1 minutes. Okay, so pretty neat. We revisited this idea from grade 11, but now we can actually solve these kinds of exponential equations. Yesterday, we learned one technique using a change of base in a question like this, where it's not possible. Taking the logarithm of both sides helps us out. Now, let's use technology to graph this one and just to kind of like see how this checks out. We starting off with 100 milligrams, and in 3 minutes it went down to 50. So I'm just going to head to Desmos. Probably a good range of values to use here. Maybe -1 to maybe 10 seems fine with a step of 1. And then let's do -10 to maybe 110. 110 with a step, get out of here, face, with a step of 10. And now let's graph our function. And maybe just off to the side here, we now actually have our function to model the amount of half-life for part B. We are starting with 100, and then a half or 0.5, whatever you prefer. And then T, we now know the half-life about 3.1. So we can graph this function and kind of look at this over time. So A was 100 times 0.5 in the exponent. I'm going to set up some brackets, and we'll do x divided by 3.1. Pretty good. So just let's make sure our graph makes sense here. So our initial value is 100. We start with 100. You can see after 1 minute, model looks pretty good. We're down to about 80 milligrams. And then our model says it takes about 3.1 minutes. And just looking at 3.1 minutes seems very reasonable. We got 50 milligrams for that, or we got the half-life of 3.1, and it looks like it's down to 50 milligrams. So everything checks out. Looks like we did a good job. And I think we can kind of tie a bow on this question. All right, so let's have a look at our second example. So we're going to expand upon this tool we have. Again, yesterday we did changes of base. This is impossible here. We cannot write 4 as a power of 3 very easily, or 3 as a power of 4 very easily, and they don't have some kind of common base we can write them as. So we can't use a change of base, or at least not easily. But we can use the technique from the previous example. We can use that power law of logarithms that we discovered last unit. We can solve this equation by taking the logarithm of each side. So that will be our starting point. We're going to take the log of each side. I might zoom in the tiniest bit here. Looks good. All right. So we'll do the log of 4 to the power of 2x minus 1 equals the log of 3 to the power of x plus 2. So how does this help us? Well, if we apply our power rule, or just say apply the power law, then the 2x minus 1 comes down in front. And we're left with 2x minus 1 times log 4. And on the right-hand side, we're going to get x plus 2 times log 3. And if you think about what we have here, we've turned this exponential equation into a linear equation, because log 4 and log 3, they're not nice round numbers, but they're just numbers. And this is a linear equation that we can solve using just techniques that we learned in grade 9. So we're going to use the distributive law to expand on each side. And so we get 2x times log 4. Now, normally we write the numbers out front. Personal preference for me is to write my log at the end. That's just how I feel comfortable. But you could say 2 log 4 times x, or like I did, 2x times log 4. Then we have minus log 4 equals, I like writing x log 3. Don't copy this down, but I don't like necessarily writing log 3 times x, because then it's you're a little unsure. Is this the log of 3x, which you could easily mistake that for? Is it log 3 times x like it should be? So to avoid that, I just prefer writing the log last. Again, personal preference. X log 3 and then plus 2 log 3. And we're just going to proceed just like our grade 9, We're going to collect like terms. So I'm going to put I'm showing a lot of work here. I'm going to put all the x stuff on the left. So we have 2x times log 4. We'll have minus x log 3. On the right, we'll have 2 times log 3 plus log 4. Leaving things exact for now. On the left-hand side, how are we going to get x by itself? Well, we collect those like terms by essentially factoring out the x. We're left with 2 times log 4 minus log 3 equals 2 log 3 plus log 4, and we're done. Dividing both sides by 2 log 4 minus log 3, we get the exact form of this solution. 2 times log 3 plus log 4, all divided by 2 log 4 minus log 3. So this is exact. Let's find the approximate value to this one. Let's get it to maybe 2 decimal places. Equals approximately. So you may choose to do this in a couple different steps on your calculator, or you may just choose to use brackets like I'm doing and punch it in all at once. It's your life. I'm not your dad. You do what you want. 2 log 3 plus log 4 divided by 2 log 4 minus log 3. And I got approximately 2.14. And this would be the approximate solution. I would expect you guys to show me the exact solution and then get the approximate solution afterwards. So I'd like both. But yeah, we can solve complex logarithmic equations like this by applying our power law and then just using techniques from earlier grades. The complication here is that we have log 4 and log 3 as part of the coefficients, but they're just numbers. So we can collect like terms, etc., just like in grade 9. Now that's an algebraic method. Of course, you can solve equations by graphing. If all you care about is the solution, yeah, we can solve this by graphing. And let's actually head back to Desmos and give this a try. Of course, you need to be able to do these algebraically. We'd like to see that. I'm just going to reload Desmos, get a fresh graph here, and let's graph each side of this equation. So we'll graph the function y equals 4 to the power of and 2x minus 1. Yeah, Desmos, make sure, I think you'll have to do brackets 2x minus 1. If you're using Desmos, just be careful with that. Plus 3, excuse me. And then for my next function, I'm going to graph the right-hand side, 3 to the power of x plus 2. All right. So our solution was at about 2.14. So I'm just going to kind of scroll up. Eventually we'll get there. Okay, so usually if you click on one of these, it's going to show you a gray dot where they meet. And here we go, 2.14. So it looks like we did a good job. And yeah, my advice to you guys, like, and whether it's on an assignment, on a test, like obviously you got to do it algebraically. But you've got technology there. Why not just check your answers? Oh, and I said 2.4. Silly me, it's 2.14. I said 2.14. I got 2.14 on my calculator. I wrote down 2.4. Okay, so kind of like a level 1 problem with the half-life, next level of problem with example 2, and we're going to take it up one notch here, and we're going to solve a pretty cool equation. If you look at this equation, taking the log of both sides is not going to help you get the variable out of the exponent, because we don't have a rule for the log of one power minus another. If the 4 wasn't there, then that'd be fine. Then we could have a base of 2 on either side and apply our method from our first lesson. This one's a bit more complicated. So I'm going to show you guys an algebraic way to solve this one, and then we'll, as we did in our second example, we'll check it in a calculator. What we're going to do is I'm going to just rewrite this. Actually, I'll rewrite it afterwards. There's no easy way to get out of the x, so we're going to use a clever trick. Now, you might be wondering, how the heck does the quadratic formula tie into this one? Well, we're going to do a little algebraic trick. Like in your grade 9 course, you don't have to write this down. But when you guys were solving, maybe you were solving an equation like this: a half x plus 2 equals a third x minus 4. A way to clear the fractions you guys learned in grade 9 was to multiply by a common denominator. And that would give you a new equation, 2x minus 24, with no fractions, with the same answer, and that's a bit easier to solve. You multiplied by a constant. We can apply a similar strategy here, but not by multiplying by a constant. We're going to multiply by a variable expression. We're going to make a very clever choice here. We're going to multiply by 2 to the power of negative x. So let me show you what I mean by that. So I'm going to take the left-hand side, I'm going to multiply it by 2 to the power of positive x. Minus 2x. And I have to do the same thing on the right-hand side, 2 to the power of x times 4. So we multiply both sides by 2 to the power of x. So why did we do that? Well, just like multiplying an equation with fractions by a lowest common denominator clears the fractions, this will clear the negative exponents, and it's going to give us something that's easier to work with. So here we go. We can show, I got the space here, so we can show a bit of work. So we'll have 2x, 2 to the power of x times 2 to the power of x. We'll have minus 2 to the power of x times 2 to the power of negative x. And on the right-hand side, we're just going to have 4 times 2 to the power of x. Not really anything we can do over there. But let's check this out. 2 to the power of x times 2 to the power of x. Our power rules for multiplying powers to the same base is to add the exponents. This is equal to the power of x plus x, 2x. 2 to the power of x times 2 to the power of negative x. Here's the beauty of this. X plus negative x gives you 0. And on the right-hand side, we have 4 times 2 to the power of x. Here, we just applied our exponent rules, right? And of course, 2 to the power of 0 is 1. So 2 to the power of 2x minus 1 equals 4 times 2 to the power of x. And I'm going to rewrite everything on one side. 2 to the power of 2x minus 4 times 2 to the power of x minus 1 equals 0. And you still might be asking, well, how does this help? And where does the quadratic formula come in? What you have to recognize, and I might just write a text box over here, this actually is a quadratic equation, but it's not quadratic in x. It's not like x squared plus a number times x plus a constant. This is a quadratic equation in which the variable is, and then I'll just write this down because my text can't do exponents too well, in which the variable is not x, it's 2 to the power of x. Because guys, check this out. I can write this equation as 2 to the power of x squared minus 4 times 2 to the power of x minus a constant equals 0. This is quadratic, and the variable is 2 to the power of x. Here's what I prefer to do at this point. To make it a little more obvious, I'm going to make a little change of variables. And I'm going to let a variable u equal 2 to the power of x. Why do I do that? Well, now I can rewrite my equation a little cleaner. U is 2 to the power of x. I'll replace it. I get u squared. 2 to the power of x is u minus 4u minus 1 equals 0. And now our strategy is kind of unfolding. We can solve this quadratic equation fairly easily. In our case here, we'll be using the quadratic formula. That will give us some values for u, or 2 to the power of x. From there, we can actually find out what x is using our skills from previous examples. So let's go about our business. Let's solve this quadratic equation for u. So u equals, negative b, which would be positive 4, plus or minus the square root of b squared. So negative 4 squared, minus 4 times a times c. A in this case is 1, c is negative 1, all divided by 2a. All right, so let's continue on here. Equals 4 plus or minus the root of, so we get 16 plus 4, which is 20, all divided by 2. And we can actually write this a little cleaner because root 20 is like the root of 4 times 5, and the root of 4 is 2. So 20 we can write as 2 root 5, all divided by 2. And then everything there can be divided by 2. And what you're left with is that u is equal to 2 plus or minus the root of 5. And we've got it. So we see apparently we have two solutions. So let's do a bit of a deeper dive, and let's actually see what x is equal to. So remember, let's actually explore that now. So we've got u, which was, remember that we use a change of variables. Our variable u was just 2 to the power of x. So what we've shown is that 2 to the power of x equals either 2 plus root 5, or 2 to the power of x equals 2 minus root 5. So let's explore each of these cases. So in case 1 here, we can solve this equation now, right? We have the tools. We take the log of each side. Log 2 to the x equals the log of whatever 2 plus root 5 is. Use our power rule. X log 2 equals the log of 2 plus root 5. And we can solve for x. X equals the log of 2 plus root 5 divided by log 2. This is exact, which is great. We want exact solutions, but let's get the approximate solution as well, because we're going to graph this afterwards and have a look. So the log of 2 plus root 5 divided by log 2. So I got approximately 2.08 as our first solution. So let's actually take a pause. We'll look at case 2 in a second. Let's head to Desmos and see if this checks out. So I'm going to head back to Desmos. I'm going to just refresh everything. I wonder if I can. There's probably a way to clear a button to clear it, but I'm just going to refresh my page. So as we usually do, we're going to graph the left-hand side and the right-hand side of this equation. The left-hand side, 2 to the power of x minus 2 to the power of negative x. Okay, interesting looking function. And then we'll graph y equals 4. Okay, and about 2.08. Now, something interesting is kind of we can see here. Like we can see our solution of 2.08, right? If I keep zooming out, like where's our other? We got a second case, right? We haven't explored yet. I don't see where this other solution is going to come from. So let's look at case 2. We're going to see something interesting. So looking at case 2, here we go. 2x equals 2 minus root 5. If you actually think about it, what is the value of 2 minus root 5? You can do it on your calculator right now. 2 minus root 5 is actually a negative number. The root of 5 is more than 2. 2 minus root 5 is less than 0. And in actuality, there is no x. There's no value for x. I could just take this out, but such that 2 to the power of x is less than 0. What our second case brings us to here is that there's no other solution. Our second case does not give us a solution. We have seen things like this when we solve trig equations. Sometimes the second case doesn't give you anything. And here, I'll just say this case provides no solution, which is consistent with the graph we just saw. No solution. X equals, I'll just maybe tie a bow on this question, write a concluding statement. The only solution to this equation is x equals 2.08, approximately. So this is interesting. So I mentioned the fraction thing earlier in clearing the fractions. In grade 9, when you multiplied by a constant, it didn't actually change the equation fundamentally. Even though it might have looked a bit different, it had the exact same solution or solutions. Here's the thing though, when you multiply by not a constant, when you multiply by something that's variable, like 2 to the power of x, that's variable. It differs depending on x. What you do is you introduce the possibility of adding an extra solution to the original equation that wasn't there before. This equation here only has 2 solutions, or only has one solution, x equals 2.08. So what we have to be careful of is when we are multiplying by a factor that's not constant, it is possible of obtaining extra roots. And here, 2x, to the power of x being 2 minus root 5, was like an extra root. It's not actually possible. So you need to actually check to see that the roots obtained actually satisfy the original equation. So here we only got one. So 2.08, you can check in the original equation. You can do 2 to the power of 2.08 minus 2 to the power of negative 2.08. You can give this a try yourself, and you can see, accounting for rounding, it gives you 4. This is very important, though, guys. When you are solving these in general, you have to check both. It may happen that you may get 2 values for x according to your math, but only one of them is an actual solution. The other guy was introduced when you multiplied by that constant function, or by the variable function. So here, one solution. In general, you should check them both to you should check your solutions to make sure they actually satisfy. And we've already graphed this one, so we actually know that is a root. Okay, so um, we know we have a second technique now for solving equations. We can take the log of both sides, and the equation maintains its balance. The equation's still an equation, and we can proceed solving from there using their power law of logarithms. And uh, in our example 3, we saw that sometimes we can use that clever trick and turn an exponential function or equation and think of it as a quadratic equation where we can use a quadratic formula, or in other cases sometimes you might have had to use a quadratic formula, maybe we could just use factoring. And we have to keep in mind, when you use a technique like example 3, sometimes this can lead to what we call extraneous roots. They're not actually solutions of the original equation. They're solutions of the new equation you made by multiplying by some kind of function. You have to go back and check all of your answers and make sure they satisfy. Now, in the McGraw-Hill Ryerson text section for this, some of these questions, especially 1 to 8, has a lot of parts. I've given you guys a lot of equations to solve. I want you guys to get comfortable with this method and become pros at it. But it is a lot of questions. So you know yourself, do as many as you need to get comfortable with the skill. All right. All right, guys, that's it for me. Hope you guys enjoyed the lesson. I enjoyed giving it. Please reach out if you need anything, and we'll talk to you guys soon.